Welcome to NTC Now, where we explore the frontier of naturetech, the technologies and solutions accelerating our path to a nature-positive future. I'm Paige, I'm the community lead at the Naturetech Collective, and each week we bring together innovators, experts, change makers who are harnessing technology to protect, restore, and regenerate our natural world. We've spent the last few weeks exploring how we gather data about nature, from ground sensors to satellite imagery. Today, we're tackling the next critical challenge. What do we do with all this information? Every day, our planet is being monitored by hundreds of satellites, generating over 100 million gigabytes of data. Add to that the vast amounts of information from ground sensors, drones, and other monitoring technologies, and we're faced with an information overload that no human team could possibly analyze manually. This is where artificial intelligence comes into the picture, our subject of the day. We're delighted to welcome Maya Pindeus, CEO of Another Earth, who's going to help us understand how AI is transforming our ability to interpret nature data at scale. Another Earth is pioneering the use of synthetic data to improve AI performance in Earth observation, addressing one of the fundamental challenges in making these technologies truly effective for AI and nature tech. Today, Maya is going to share insights on what makes AI and nature tech unique, the challenges of training these models, and how organizations are already using these technologies to better protect nature and manage risks. So whether you're a sustainability professional trying to understand nature-related risks, or a conservation practitioner trying to enhance monitoring capabilities, or a technology provider interested in new applications, today's conversations will provide the valuable insights into how AI can serve nature protections. So Maya, thank you for joining us. I'd love for you first to introduce yourself and your startup to our community and audience.
Paige. Hi, everyone. Glad to be here. My name is Maya Pindeus, and I'm the co-founder of an organization called Another Earth. So here it is really about building technologies that enable AI for Earth observation, AI for nature tech at scale. So the way we do that is that we develop a synthetic data engine. Essentially, I will dive a bit deep into what is this synthetic data, but essentially we generate training data, testing, validation data that allows you to train your AI models and then apply them on this whole massive population of Earth observation data, satellite data, aerial data is being collected every day. It's really about making Earth observation more accessible and AI in Earth observation more scalable. The key question for me is how do we actually enable better insights from space, right? So we have to imagine that there are all these data points, essentially snapshots of any given moment being collected. Satellite constellations monitoring the surface 24/7. And satellites only amount to more than 100 million gigabytes of data collected per day. And this does not even include other data sources such as drones, aerial data, and other remote sensing data. So these are huge amounts of data. And in order to implementing AI and helping, generate insight, we're facing a couple of specific challenges. So one is the Earth's surface is incredibly complex, right? There's so much different information that can be extracted, is being extracted. And the further you dive into a satellite image, for instance, the more you can see and the more you can extract. And that's, exciting and part of the opportunity, but also part of the challenge. And then the second challenge is that things are changing so fast, so rapidly. So we're regularly experiencing new events, new risks, natural hazards, natural phenomena that we need to adapt to. And it's really important to learn how to recognize, predict, and adapt to these quickly. So AI has this huge potential there to be applied to this data, generated and collected from space. But the thing with AI is that it's only as good as the data it is trained with. So more than 90% of its success actually relies on training data. So essentially, in order to build and implement AI for Earth observation, for nature tech, we do need to make sense of this data first. That means to convert raw data, the heaps of data being collected by satellites and other sensors, into powerful data sets. So those data sets need to apply or need to refer to specific nature events in order to build an AI model. So for instance, to give you a couple of examples, whether you're looking to understand the impact of a flooding event, or trying to predict the likelihood of a wildfire, or you're looking to protect assets and utilities, or you're looking to measure the success of an afforestation project. The AI models able to address these challenges, they need to be trained, tested, validated on specific data sets that reflect this particular problem we're trying to solve. So essentially that, to give you an overview of the challenge and also of the opportunity, but also diversity of the data that we're dealing with. So essentially we need highly customizable data sets. It's almost the first really, really important point. They're able to address very diverse and rapidly changing environments and the challenges a planet is facing. So very often we're actually dealing with creating data where there is none yet, despite all the raw data being collected, right? The satellites collecting data because we're looking for events that maybe that are emerging, that are starting to happen with occurrence, they're adapting very quickly. So all of this needs to be encompassed in order to make sure that we train highly resilient AI models. Nature systems are highly complex and almost like intricate, right? And they constantly change. So actually tracking and making sense of these changes is one of the key needs for AI and nature tech, in my view. And we've seen, similar phenomena in other industries, and it's definitely true to other industries as it is to nature tech, that there's just no one size fits all approach or application. So I believe it's not right to expect an AI model to be able to solve and tackle all of these challenges because they're so specific, they're so bespoke, they're changed so much. Maybe a small thought exercise. If you just picture a satellite image of, let's say, Greater London. Okay, so the city, the green belt, the outskirts, in satellite imagery. Depending what you're looking to train an AI model for to see, it could derive a range of different insights. So, for instance, you could track urban changes, you could monitor the electrical grid, could check anomalies incidents around railroads and public infrastructure. You could monitor protected species around London's greenbelt. You could understand insulation types for energy performance, of building performance, predict adverse weather conditions, and many, many more. So I think that is what makes AI and nature systems so special, really, that the challenges are so manifold, and it requires a lot of, I think, interconnected systems and collaborations to be able to address all of these. And I think this also really illustrates the opportunity, because if you're able to be able to collaborate and build AI systems that can address these fast changing and fast paced changes, I mean, that's the benefits and the impact, positive impact can be huge. Yeah, so on one hand, just to hone down on the data set part and topic, again, it requires specific data sets to encompass the full diversity of what we're looking to find, of the scenarios, essentially. So that means that the models need to be able to understand specific occurrences, but also be general enough to not only, be fitted to specific occurrences. It requires a set of different data sources. If we just look at satellite imagery, there's many different constellations, many different spectra of those. And then with the data sets, right, with the training data sets, it requires models that are interpretable, meaning manageable in size as well, where you can actually understand why a decision or why a suggestion, why an interpretation has been made, to then, want to derive action from it, but also create a feedback loop and make sure that the data that is feeding the model is up to date on one hand, but also the models that are constantly interpretable, and we can understand why things are happening, why things are decisions are taken, and then take action. It also creates trust, right? I think that's a really important one as well. Trust in the community of how to collaborate, how to work with these systems. So I think that this is where we look at diversified data streams, right? Making sure to work and also the work with we do with Earth really comes in and saying where there's not enough data, where we need to generate training data sets for specific or testing data sets, for the matter of fact, for a specific challenge, for a specific application, we can also generate these synthetically, artificially, essentially, by being able to create a very diverse data set, right? So on one hand, diverse data sets for a specific application, for a specific challenge, and also data sets or data that actually allows you to, where there is none so far. I mean, rare objects, rare events, for instance, right? Areas that are, obstructed by cloud coverage, for instance, natural disasters that have, and started occurring a certain frequency, to generate this data, to train models to be able to actually find those patterns and to actually find those information in the actual raw data. So maybe it's worth that also explaining how we talk about and think about synthetic or like training data here. It's about making sure that a model is fed with the right distribution, the right detailed information it needs to perform well, but then also to be able to be applied to all the raw data that is being collected, because a lot of the information is somewhere in there, right? There's so many satellites, there's so much observation data. It's just about how do you train a model to actually find that, how to train a model to actually be applied to that. When I think of synthetic data, it's essentially a way of generating large amounts of, in our case, imagery, right? Because we're working with Earth observation data, Earth observation imagery that is exactly calibrated and tuned so you can train a model with it, then apply it to the hundreds of millions of gigabytes of raw satellite or Earth observation data. So that's where this is where we fit in the chain. And some of the benefits there is that you can essentially help train AI models or help AI models see a lot of the detail that might not be visible with human eye, might definitely not be easy to find in raw imagery. So for instance, if you like looking at certain things like anomalies, right? Or if you're looking at, again, at changes on the Earth's surface as they relate to nature disasters, for instance, as they relate to other examples, deforestation or afforestation projects, understanding and tracking changes in a lot of detail requires specific data. And this specific data is essentially what we're generating synthetically. And with that, then train a model. And the challenge, and I think the challenge and where, the opportunity here as well is that it's important to make it scalable, because I've been, I think, talking a lot about specific data, and it might, make even an impression as or the wrong impression, I think, that everything needs to be completely bespoke. Yes, it does, but you need to define technologies, build technologies that are able to do this scalably, generate bespoke data or bespoke models while being able to be transferred, generalized, and applied to different use cases. And this is where synthetic data is so exciting. Essentially, that what we do is a data engine. So that means it's trained, it's built to be able to serve a wide bandwidth of use cases. So whether you're looking, for instance, to understand crop diseases, for asset protection crop diseases, you can generate the data for that. Or if you're looking at mining applications, for instance, a different one, if you're looking to really understand biomass, for instance, from very high resolution data, that's another example. Or you're likely to track changes in urban fabric. So those are very different examples, require very different data sets, but this can be actually served by synthetic data engine. But one thing again to say there, it's never about replacing real data. It's about enabling the use of real data and enabling the fast use and to be resilient to changes and to be able to adapt to changes rapidly. So when we think of extracting, let's say extracting insights from satellite data, right? So the first thing that needs to be done is that you essentially prepare this training data set, right? So an AI model needs to be trained on what it needs to, essentially something that it then needs to find in the, let's say, in the real world, in the world. So if we're going at crafting this training data, we work with things like masks and labels. So you need to essentially dissect the image into certain areas of interest. Remember the London example I gave you earlier. Maybe if we look at understanding, protected species in the Greater London Greenbelt, for instance, then you need a certain set of images, in the thousands, so tens of thousands, depending of the occasion, where you actually highlight, label essentially, those different species that you're looking to recognize, that you're looking to count. And that's the training data set. So as a result, you have large amounts of imagery that reflects exactly that. And then you feed this into a model. And this model can do things like potentially count, recognize, classify, particularly track changes and many other things. And that then outputs information that is then, that valuable information essentially that allows you to track changes again, to really understand what is going on in a certain region. So you validate it by essentially in the whole process of generating the whole R&D process implementation, where you constantly make validation steps against real data. So that's something that we constantly do. Whatever we generate synthetically, it's almost like like a lab probe in many ways. So you compare to real data and you compare to synthetic variations, and you make sure that the quality is applied. Only then you move on to the next step. And that's also one thing that I'm talking about, the interpretability. Only then you can actually do that, right? If you actually know what's going on in a model. And also with generating a synthetic data, it's also, a range of models. So you really need to make sure that you're constantly able to compare. And that applies to the quality of the performance, to the quality of the target data, right? Which constellations, which satellite resolutions, and so on. So what we're seeing more and more is that organizations are in need to really adapt to fast changing events. So those are climate events, those are the need to ensure assets and infrastructure to make sure they're resilient, they can weather these changes, and that organization can actually understand what is going on. So a key motivation is to have a more complete picture of what is happening around organization assets. And I use the term assets in the widest possible sense, right? Assets ranging from agricultural assets such as crops to urban infrastructure, to energy and utility infrastructure like the transmission lines and so on. So the goal is to understand and adapt to the impact of fast changing events and to get a better view of the likelihood of those events happening in the future, to mitigate losses, to increase resilience, to be able to adapt. And this is really what it's all about, adapt to a fast changing environment and get a complete picture. Mm-hmm. So when we look at key applications, for instance, right? Anomalies, diseases, for instance, in an agricultural asset context, being able to assess, understand crop diseases for rare crops, or for crops that are for crops that are critical for things like importing, the nature finance sector in that sense, and to monitor agricultural practices. There you need specific data sets for regions. You need data to be able to train a model to recognize and understand diseases, for instance. And this relates and simulating scenarios. That's a really, really, really important one as well. So this relates, of course, to the finance sector, insurance sector, and the wider food supply chain. Another thing is the understanding and assessment of risks as they relate to natural disasters, to be able to understand the impact of wildfires or landslides. So essentially, how could the effect of natural disasters, how do they impact claims and how do they impact losses? So obviously insurance industry and reinsurance industry is that's a big factor here. And simulate scenarios, how could they impact claims in the future? How do they impact underwriting models in the future? So there it's really about characterizing and understanding what has happened and what is likely to happen next. There again, you need up-to-date data, right, of the events and simulations of what further events could look like, because very often you don't have historical data for events like that. So that's a really, really important use case and application in AI and naturetech. And finally, really looking back at like kind of anomalies or like monitoring it's monitoring critical infrastructure such as transmission lines or power plants. So that, of course, as it relates, as serving the population with energy, but then also understanding the impact on vegetation around or the impact for vegetation around those. There again, it's about monitoring, tracking, but again, predicting the likelihood of something happening. So as you can see, it's always about understanding the big picture, building data to train models to see what has happened, what is the status quo, and then predict the likelihood of certain scenarios happening. And the scenario building is a really interesting one because sometimes we don't really know what scenarios, there's new scenarios coming up all the time, and that's part of this fast-changing environment. I do really believe in a balanced use of AI. So essentially, yes, generalizing, yes, scaling, but addressing specific challenges. And it requires a collaborative approach, right? So a lot of what I've been talking about today, I think it's a really, really big part, like the data part, but it's one piece in the puzzle, right? So it requires organizations that do further modeling, that do the application, to the implementation, then the use by the wider public. So it also requires a lot of education still, right? But that's a collaborative effort. That's the whole naturetech community, as well as being able to think of new application areas. Because one thing that excites me the most about AI naturetech is that we're just at the beginning. So we're just at the beginning of understanding what can be done with AI because there's so many different factors. There's more data, wide availability of raw data, further detail, higher resolutions, and so on available, meaning that the insights and the predictions that we can derive from those, a lot of things we don't really know yet, that we will be uncovering those. And I think that's something incredibly positive, incredibly exciting, but then it requires effort and requires a community promoting those and promoting the responsible use of it. I believe that much more open source data will be helpful. Think about what just the impact of the Copernicus and Landsat programs that Copernicus, the European satellite constellations have. Like everyone can access those and work with those, and having much wider availability, not just of those, but of actually more high resolution, detailed data. Now I'm talking about raw data, right? That already would have such a huge impact. And then when we're talking about specific, the training data, specific data sets for rare events, for specific regions, for remote regions, having much more of a way of exchanging and collaborating on those, I think there would be a big leap for the industry, 100%.